The last class we identified that uh, defects are essentially the imperfections that disrupt the perfect crystalline order. And we mentioned that there are defects which are characterized by their dimensions in which they exist. Zero dimension defects includes point defects, and within point defects we have different categories: a vacancy where an atom is missing from the position where it should have been. An interstitial defect or a self-interstitial defect is a defect where an atom gets entrapped into the interstitial or the void space present within the lattice. And then there are substitutional defects in which you have uh, substitution taking place from the lattice position, and there is interstitial substitutional defect. There's a lattice substitutional defect and an interstitial substitutional defect. Again, the criteria for those defects. So these are the points that we covered in the last slide, and we looked into uh, the, uh, the formulation to calculate the equilibrium number of vacancies, which is highly dependent upon temperature. And we looked into how we characterize the uh, composition in a solid solution in weight percent and the atomic percent. This is what we covered in the last slide, last lecture. Today we'll be exploring the one-dimensional defects, which are known as line defects, and they're also known as dislocations. There are two categories of dislocations that we'll be looking into. Furthermore, we'll have 2D defects. The most prominent is the grain boundary defects, and then the bulk defects, which includes the pores and cracks. So, starting with the line defects, we essentially have two types of line defects. They are known as edge dislocations and screw dislocations. These are the two dislocation or line defects that we'll be looking one by one. So, how do we characterize an edge dislocation? Edge dislocations, the edge dislocation can be easily visualized as an extra half plane of atoms in a lattice. So there's an extra half plane of atoms present within the lattice that leads to the edge dislocation. For instance, you see this image over here. Can you find out an extra half plane of lattice that is present within this crystal structure?
From nature, it goes also in the multiple added.
Yes. So if you see over here, this is an extra half plane of lattice that is being inserted within this crystal structure. If you see, there are one, two, three, four, five, six columns of atoms over here, and if you see one, two, three, four, five, six, this is an extra seventh half plane that has been inserted into this lattice. And if you see, this is a plane, an extra half plane that is present there within the uh, crystalline lattice. This is creating an edge dislocation. Now, the dislocation is called a line defect because the locus of defective points that are produced in the lattice by the dislocation, they lie along a line. How? If you see here, you have a line, and these points, the dislocation, the defects, they lie along a line that is being produced in the lattice. That's why this is known as a line defect. And this line runs along the top of the extra half plane. So if we have a look at this line, this line is actually running on top of the extra half plane that is there within the lattice. The interatomic bonds are significantly distorted only on the immediate vicinity of the dislocation. So if you see these bonds over here, they are distorted. That means if you see over here, this bond is roughly same, roughly same, roughly same. But if you look at these bonds, they are distorted in different directions due to the stresses created by the insertion of this extra half plane. So within the vicinity of this defect, there is a inherent uh, stress that is being created, and we'll look into how this stress is basically related to the presence of the extra half plane, how the stress is distributed within this extra half plane. So far, is it clear?
Yes, sir.
Yes,
All right.
sir.
All right. Now, there are
सर
certain things that GG.
सर आप अगर एक स्लाइड पीछे जा सकते हैं। सर आपने बोला कि ये जो इधर आपने ये जो लाइंस बनाई है कि स्ट्रेस उधर हो रहा है।
जी
सर व्हाट अबाउट द टॉप? मैं अगर उधर भी अगर देख रहा हूँ तो उधर भी थोड़ा बहुत डिस्टॉर्शन तो आ रही है।
You can say that this is the region in which the stress is being created. The point is the stress that would be created would be in the immediate vicinity of this dislocation line. As you go far away from this dislocation line, there would not be any effect of this defect. All right.
सही, ठीक है सर।
Great, great. So now there are certain things that you need to understand about the defect. This is the same schematic, just we have looked, or we are looking from the defect from the front. We are not looking into the lattice, which is going into the screen. So how do you define an edge dislocation? You define it with a T sign or an inverted T sign. But where do you have to insert the T? This is an edge dislocation. You have to insert the T. The first line or the straight line of the T is representing the location in which the plane has been inserted, and where this extra half plane ends, you would mark it with the straight line or a perpendicular cap line. Is this clear to you? So this is basically, this line is essentially representing, this T sign is essentially representing that there is an extra half plane which is inserted from the bottom and it ends up here. All right.
सर एक
See,
बार फिर से रिपीट कीजिए। आई एम सॉरी, मेरी इंटरनेट में डिस्टॉर्शन आई थी।
what I'm trying to say is that what is the symbol for edge dislocation? The symbol for edge dislocation is this sign. This could be in a way it is visible to you, or it could be inverted. When would this sign be in a normal T notation? When the extra half plane is inserted from the bottom and it ends up here, you'll have it as a regular T. If the extra half plane would have been inserted from this side, you would have the inverted T sign for the edge dislocation. So the location from where the plane is inserted would basically define how the sign of edge dislocation would be presented. All right.
यस सर।
All right. Great. Now, what is the measure of lattice distortion? The measure of lattice distortion is basically defined by B, letter B, which is slip or Berger's vector. This is basically the measure of the edge dislocation. How do you measure it? Let's say you you're standing at this point and you have to move around the dislocation to close the loop. So let's say I am standing over here. I move one step to the left. So I'm moving one step to the left, and then I'm moving one step upwards and then two step upwards to two step upwards. All right. So far, is it clear?
यस सर।
Then I move one, two, three steps to the right. All right.
Yes, sir.
Then I move 2 steps downwards, and then I move 2 steps to the left. Now, up till now, all the steps that I have moved, they would cancel out each other. How? These 2 step upwards would cancel out these 2 step downwards. These one left and two left makes 3 step left, and I have moved 3 steps to the right, they would cancel out each other. I am standing at this point and I started from this point. In order to move or in order to close the loop, I have to move 1 step to the left.
Left.
So this extra step that I have to move in order to close the loop around the defect, this, I would say it again, this 1 step extra that I have to move in order to close the loop around the defect is basically the measure of lattice distortion or Berger's vector. Clear enough?
Yes, sir.
All right. So
सर जरा फिर से रिपीट करने की क्या था?
बेटा आप मुझे बताएं क्या था?
ये अभी जो आप बता रहे थे सर बर्जेस वेक्टर क्या था?
यही मैं आपसे पूछूं जो मैंने बताया, आप मुझे रिपीट करें कि मैंने क्या बताया आपको?
आप बर्जेस वेक्टर के बारे में कुछ बता रहे थे।
आप तो बेटा सो रहे थे जब मैं बता रहा था आपको। How did I start explaining? G, how did I start explaining?
सर मैं सिर्फ वो पूछ रहा था आखिर से जो आप क्या कह रहे थे कि सिर्फ हम इस जो है रेड वाले से ग्रीन वाले तक जाएंगे तो उसको बर्जेस वेक्टर कहेंगे।
मैं आप शुरू से बताता हूँ। आपको ये चीज समझ आई है? यू हैव यू अंडरस्टूड दैट वी स्टार्टेड फ्रॉम दिस पॉइंट वेयर आई हैव मार्क्ड माय
सर वो समझ आ गया है कि आप कह रहे थे कि जो हम सिर्फ जितनी भी लेफ्ट और राइट डिस्प्लेसमेंट्स हैं एक दूसरे को कैंसिल कर देंगे, अप और डाउन डिस्प्लेसमेंट्स हैं वो भी कैंसिल कर देंगे। लेकिन आपने जो आखिर में जो कहा था ना बर्जेस वेक्टर,
मैं बताता हूँ, लेकिन अगर जब ये सारी कैंसिल हो जाएंगी तो हम कहाँ पे स्टैंड करें? अगर मैं यहाँ से मूव, दिस इज द स्टार्टिंग पॉइंट, इफ आई स्टार्ट फ्रॉम दिस पॉइंट और मैं स्टेप्स बैलेंस करके डिफेक्ट के अराउंड मूव करके आता हूँ, तो वेयर वुड आई बी स्टैंडिंग? यहाँ पे रेड सर्कल पे।
यस सर।
जी
यस सर।
ऑलराइट। नाउ इन ऑर्डर टू क्लोज द लूप, अगर मैंने लूप को क्लोज करना है तो मुझे यहाँ पे मूव करना पड़ेगा, एक स्टेप लेफ्टवर्ड, एक्स्ट्रा स्टेप।
यस सर।
इज दिस क्लियर?
सर
So what I was trying to say is that the extra step that I have to move in order to close the loop is basically the Berger's vector. All right, or it
यस
is
सर। ओके
the
सर।
measure of lattice distortion. Clear?
यस सर।
सर इसमें लूप की डायरेक्शन क्लॉकवाइज लेना लाजमी है या कहते हैं एंटी क्लॉकवाइज भी ले सकते हैं?
ले सकते हैं, that doesn't matter. Berger's vector आप ये भी कह सकते हैं, ये आप ये भी कह सकते हैं, ये clear?
सर
All right. Now, how do you define Burgess vector? It is the displacement vector that closes the loop while traveling equal number of lattice steps around the defect. So ये जो extra step है, that is required to close the loop in order to while you're moving equal steps around the defect. लेकिन you have to make sure that you're moving around the defect. ये ना हो कि you start moving from this point, either, either, then it's already closed, but the defect was not enclosed in this movement. Clear? Is this point clear?
Yes, sir. Clear.
यस सर।
यस सर।
All right. Then you need to understand that B, which is the measure of lattice distortion or Burgess vector, is perpendicular to the dislocation line. Your dislocation line is this line. All right. Yeah. If you're looking at the front face of the lattice, if this is your lattice, going deep into the material, so your Berger vector is essentially perpendicular to this line. Clear?
Okay, sir.
ये आपकी डिसलोकेशन लाइन है ना बेसिकली स्क्रीन के अंदर जा रही है एंड this Berger vector would be essentially perpendicular to this line. Now, referring to the stress that is being caused by the presence of an edge dislocation. If now you see the sign, since the plane has been inserted from the top, you have an inverted T. अच्छा आप मुझे ये बताएं कि in this region atoms are they closer or are the atoms closer in this region? The upper region or
Sir, upper
lower?
region.
Upper region
Bottom.
में atoms जो है closer है. किसमें ज्यादा closer है?
Sir, in upper region.
अब
Alright.
देख तो अपर
और lower region में क्या है?
upper में
Far.
further
Sir, far separation type है थोड़ी सी.
ठीक है? They're far away in the lower region. Alright? Clear?
Yes, sir.
So the upper region would have compressive strain. Alright? As if the atoms are being compressed together. And the lower region would have the tensile strain, as if the atoms have been stretched apart. Alright?
Yes, sir.
Alright, great. Alright, now if this is clear, we'll now move on towards the screw dislocation. Now, edge dislocation was rather a simpler defect to visualize. Screw dislocation is a defect that is somewhat difficult to imagine. The screw dislocation is slightly more difficult to visualize. To visualize a screw dislocation, imagine a block of metal. So you have a block of metal over here, and I would start applying stress on this block in this direction and in this direction. It's a shear stress that is being applied onto this uh, block of metal, and shear stress is applied across one end so that the metal begins to rip. अगर मैं सिर्फ इस एंड के ऊपर आई एम अप्लाइंग द shear stress on this end, ये जो है ये ऐसे जैसे यू स्टार्ट रिपिंग अ पेपर जैसे फाड़ना शुरू करते हैं ना, ऐसे ऐसे ये इट वुड स्टार्ट रिपिंग इन दिस डायरेक्शन. इज दिस मेकिंग सम सेंस? कोई समझ में आ रही है ये चीज?
सर इसका ये मतलब है कि हम ऊपर वाली प्लेन को नीचे वाली प्लेन को इन ऑपोजिट डायरेक्शंस मतलब हम उसको फोर्स कर रहे हैं.
फोर्स कर रहे हैं बट ओनली ऑन दिस एंड. ऑलराइट
सर upper and bottom.
Upper and bottom end they are being sheared but only at this corner.
अच्छा सही ठीक है.
I'll
Only
show
at
you an image that would make it clear, but ये चीज अभी clear है? Is this clear to everybody?
Yes sir.
All right. So what would happen would be is that this would start shearing apart. Making sense? Now, if you look at the image, is it making sense that this layer would move in this direction? This layer would start moving in this direction, and it would start ripping. जैसे कि if you are tearing apart a paper, आहिस्ता आहिस्ता ये tear apart हो रहा है. Is it clear?
Yes, sir.
All right. Now, if it is tearing apart, there are two surfaces that are basically separating. एक तो ये surface है जो कि lower surface है जो इस block के साथ है. All right. जो आपको नजर आ रही है. Is it clear?
Yes, sir.
एक वो surface है जो कि it belongs to this block, और if you are standing over here and you look upwards, तो आपको सबसे पहली surface जो नजर आएगी वो surface होगी जो कि इस block के साथ है. Clear?
Yes.
Is this point clear?
ठीक है
नहीं है तो
सर.
बताएं. नहीं है तो बताएं.
सर इसका ये मतलब है कि एक ही ब्लॉक का ऊपर वाला पोर्शन और नीचे वाला पोर्शन मूव हुआ है.
बिल्कुल. Right now I'm just trying to make you understand that there are two surfaces, two separate surfaces. One of the surface is if you are standing over here at this green dot and you start looking upwards, तो इस ब्लॉक की जो ये लोअर सरफेस है जिसको भी मैं दिखा नहीं सकता आपको, that would be the surface that you'll be looking at. That is one of the surface that is ripping. जो ये जिसकी आउटलाइन होगी जिस सरफेस की, अगर मैं
ठीक है
ये
सर.
ऐसे कर लूं तो ये सरफेस होगी जो कि अभी हमें नजर नहीं आ रही. क्लियर है?
यस सर.
और दूसरी सरफेस जो है वो कौन सी सरफेस है? द अदर सरफेस इज द वन दैट इज एग्जैक्टली टचिंग इट. वो ये सरफेस है जो कि इस ब्लॉक के साथ है. इज दिस क्लियर?
यस सर.
ऑलराइट. Is it clear to everybody?
Yes, sir.
All right. Now, the image to the right shows the plane of atoms just above the rib. So, what we are saying is that we are looking at the layer which is essentially ये जो layer है, if you are standing over here and looking upwards, this layer is essentially shown over here. Clear?
Yes, sir.
All right. Now, if there would not have been any shear stress, atoms would essentially be lying at these positions. All right. अगर shear stress ना होता तो एटम जो ये मैंने ड्रॉ किया है इस पोजीशन पे लाई कर रहे होते. Is it clear or not?
Yes, sir. Clear.
ठीक है सर. क्लियर है.
अगर ये एटम सारे जो हैं वो सारे इस लाइन पे लाई कर रहे होते. Now, what has happened due to this shear, the shear that you have applied? Some of the atoms which are appearing in this red color, or atoms which are appearing in the red color, they have moved a complete one step, complete atomic distance. These red atoms, they have moved complete atomic distances and they have acquired new positions. Clear है? एटम जो यहाँ पे पड़ा हुआ था वो एक कंप्लीट एटॉमिक डिस्टेंस स्पेसिंग मूव कर गया. इज दिस क्लियर?
यस सर.
Yes, sir.
और these blue atoms, they are the atoms which have not experienced the shear stress at the moment. Clear?
Yes, sir.
यस सर.
And the green atoms are the atoms which are somewhere in between at the moment. They have moved from their original position, but they have not acquired a complete atomic distance movement. Clear?
Yes, sir.
All right.
Yes, sir.
So it says the blue atoms represented the circles, which the atoms which have not moved from their original position as yet. The atoms represented by the red circles have moved to their new position in the lattice and have re-established metallic bond. They have recreated their bond. And the atoms represented by green circles are in the process of moving. All right. Is this clear to you? The point is clear to you guys?
Yes, sir.
And
Yes,
if
sir.
if I draw this line, the red line, behind this line, there is no defect. Ahead of this line, you have the defect that has been created. So you call this red line as the screw dislocation line, and the symbol is this curly arrow that represents the screw dislocation. All right.
Yes, sir.
Now, how to measure the the amount of screw dislocation? Again, as we measured in edge dislocation, it was a single step to the left. That was the Burgess vector. In screw dislocation, you would move around the defect in this loop. So I am moving from a region where there is no defect. I am moving from a region where there is no defect. I am moving in a region where there is defect and coming back to the same point. So if I start from this blue dot, I move 1, 2, 3, 4, 5, 6 steps forward. So I'm moving 6 steps forward. Then I'm moving one step downwards, one step downwards, one step in this direction. I said, let's say one step out of screen. Then again, I'm moving 1, 2, 3, 4, 5, 6 steps backwards. And then I'm moving one step upward to close the loop. So 6 forward, 6 backward would cancel out, 1 downwards, 1 upward would cancel out. There is one step out of a screen that you're moving. That is basically the measure of your uh, uh, the measure of your screw dislocation. So this is the Burgess vector B, which is representing the amount of defect that has been created due to the screw dislocation. Clear enough?